Okay, here we are. Good morning to everybody. Today, and in the next lesson, we will address a classical diffraction problem, the so-called Sommerfeld-Half plane problem, which is described in short here. Basically, we have a uniform plane wave that impinges normally on a half plane, which is assumed to be perfectly conducting, with the electric field parallel to the rim of the half plane. So here we have the arrows that indicate the direction of the electric field in red, the unit vector in particular of the electric field, which is parallel to the rim of this half plane. Well, that's not a half space, that's a half plane. So it's parallel to the y-axis in this reference frame. Then there is the unit vector that gives us the direction of incidence of this uniform plane wave. And finally, the unit vector in blue that indicates the direction of the magnetic field. So this is a linearly polarized plane wave. As you can see, the x-axis runs along the perfectly conducting half plane, whereas the z-axis is orthogonal to such an half plane. The incident angle is defined with respect to the z-axis, and it's indicated with the symbol theta I, so that we can write down the electric field for the incident wave, as you can see here, as a complex amplitude, E0I. Then there is the unit vector, E0I, which is the same as the unit vector of the y-axis. And finally, we have the dependence on the coordinates, which is a simple exponential, since we are dealing with a plane wave, where in the exponent you can see the appearance of the incident angle. The dependence, of course, is only on the x and z coordinates, since this is a normal incidence with respect to the y-axis. The problem, the diffraction problem that Sommerfeld addressed, was that of finding the total field everywhere. And the total field in any diffraction problem is the sum of the incident field, which is given, plus the scattered field, which is the unknown of the problem. Well, some historical remarks. Sommerfeld was the first to find a solution to this problem, and he did that in the paper that is reproduced here in its initial part, the mathematical theory of diffraction. It was written in German, and it appeared in the mathematical annals at the end of the 19th century, as you can see from the reference reported there. Now, Sommerfeld obtained his solution in a quite mathematically elaborate method, using a method which was quite involved, and it was not particularly suitable for addressing different kind of problems. However, it was historically very important, provided the first exact solution to a diffraction problem, in particular the problem of a perfectly conducting half plane. Later, some decades later, it was realized that this problem could also be addressed with the Wiener-Hopf approach that had been developed in the 20s and 30s by Norbert Wiener and Jan Hopf. In particular, Edward Copson derived the solution for the Sommerfeld half plane problem in a paper that appeared in 1946, which was followed by other contributions. For example, this paper by Carlson and Heinz, in which the problem was generalized to that of scattering from an infinite set of metal plates rather than a single one. Shortly after that, in 1951, Clemau derived an alternative approach, which was basically equivalent to the Wiener-Hopf approach. It was based on the formulation of the so-called dual integral equations, which was somewhat advantageous because it was shorter in its derivation, since it dealt directly with the angular spectra of the involved fields. And actually, this approach is the one that I will expose at the end of this lesson, and the motivation for introducing the Sommerfeld half plane problem is precisely that of illustrating the Wiener-Hopf approach in its dual integral equation version. However, before doing that, we will address many other things. In particular, consider that much later than those years, in particular at the beginning of the 80s, Professor Franco Gori from Sapienza University at that time, then he moved to Roma Tre University and now he's retired, he was able to find a much simpler solution to the Sommerfeld problem in terms of simple cylindrical functions having a half-integer order. This was published in a paper in 1983 on optics communications. And this is actually the solution that I will illustrate first in the first part of this lesson. But before doing that, let me introduce some general remarks about the Sommerfeld problem in the next slides. Okay, first of all, let us examine a bit more closely the problem I formulated before. Consider that the perfectly conducting half plane, which is reproduced here in the box, is a structure that is translationally invariant with respect to the y direction. So this is a first geometrical consideration. Furthermore, the incident field is also independent of the same y coordinate, and furthermore, it is polarized transverse magnetic with respect to the y-axis. As you can see from the unit vector that represents the magnetic field, we have no component of the magnetic field along the y-axis, whereas the electric field is parallel to the y-axis. So from these first two remarks, we may derive some consequences. First of all, that the scattered field, and therefore also the total field, which is the sum of the incident and scattered fields, is also independent of the y-coordinate, and it is also polarized Tm with respect to y. And furthermore, the only non-zero components of all these fields are Ey, so the component of the electric field parallel to the rim of the half plane, and the transverse components Hx and Hz of the magnetic field. And finally, for this kind of field, if you write down explicitly the Maxwell equations in rectangular coordinates, you will find that it is possible to express the two components of the magnetic field in terms of the single non-zero component of the electric field Ey. In particular, Hx is proportional to the derivative of Ey with respect to z, whereas Hz is proportional to the derivative of Ey with respect to x. Okay, having said that, we may consider also what happens right on the back half plane. On that half plane, there will be a surface electric current that flows, which is related, as we know, to the jump of the tangential component of the magnetic field through the usual relation z0, which is the unit vector normal to the half plane, times, this is a vector product, the difference between the magnetic field on the positive and negative sides of the half plane. If you develop the algebra, you will find that this surface electric current is parallel to the rim of the half plane, so it's parallel to the y-axis, and its amplitude is proportional to the jump of the x component of the magnetic field, which by Maxwell equations, as we said before, is also proportional to the derivative of Ey with respect to z. So basically, since we know that the incident field is that of a plane wave, and that field is continuous along with its derivatives everywhere in space, here we have a jump, so the only thing that jumps can be the scattered field, because the incident field is continuous. So in these square brackets, you can insert directly the scattered electric field, which is discontinuous, therefore, across the perfectly conducting half plane. And of course, this discontinuity is related to the existence of this surface electric current, okay? Well, the problem can be now formulated mathematically, since we are dealing with a two-dimensional problem in that there is no dependence on the y-axis. We have basically a scalar problem in which the unknown is the component, the only non-zero component, Ey, of the electric field. And in particular, the unknown is the scattered electric field. If we let D, this calligraphic D, be the region which is occupied by the perfectly conducting half plane, so we are on the plane z equals 0 for positive values of the abscissa x, positive or equal to 0, then the formulation of the problem involves, as you may suspect, the ubiquitous two-dimensional Helmholtz equation, that is the Laplacian, made with respect to the transverse variables x and z of the unknown, that is the y component of the scattered electric field, plus kz squared, k0 squared, times the unknown. This is equal to 0, and this holds everywhere in the xz plane, with the exception of the perfectly conducting half plane, where we have discontinuities. And on that half plane, instead, we will enforce a boundary condition. The boundary condition is that the total electric field, which is purely tangential with respect to the half plane, must vanish. So this means that, in other terms, the scattered field must be equal and opposite with respect to the incident field. So in this case, since we have a plane wave, the y component of the scattered field must be equal to minus E0i, the amplitude of the incident wave, times the exponential that describes the propagation of the incident plane wave on the plane z equals 0. So there you find only the dependence on x of this plane wave, that is e2 minus j, k0, sine, incident angle, and then the x coordinate. So this is the formulation. Actually, these equations are not sufficient to have a unique solution in this problem, because we must also say something about the neighborhood of the rim of the half plane, because the rim of the half plane is a discontinuity or a singular part of the geometry. In particular, we need some edge condition in order to ensure the uniqueness of the solution. There is some information about the behavior of the field in the vicinity of the rim. So now here I have drawn a general situation in which we have a wedge made of some material, for example, a perfect conductor. This is represented here in gray, with some internal angle alpha that would be equal to 0 for our problem, since we have a half plane. Then the usual coordinates. In addition, we have the polar coordinates, rho, which is the distance from the rim or the edge of this wedge, and phi, the angle in polar coordinates. What we can say in general about the behavior of the electric and magnetic field is that it can be represented by some series in a neighborhood of the edge, which could be written for this kind of problem, for example, for a perfectly conducting wedge, in the form of a power series, in which, however, we have explicitly written in front of the power series some power, some possibly non-integer power of the transverse coordinate, radial coordinate rho. So we have rho to the power Greek n, for ni, times an ordinary power series with coefficients a0, a1, and so on, so that the dominant term in the limit when rho tends to 0, so we are very close to the edge, is the first one, which contains the power ni in the exponent. If you use Maxwell equations to derive the magnetic field, you will find that the magnetic field has a dominant component in its power series that goes with a different exponent. The exponent is ni minus 1. Now, the point is that to have uniqueness of our problem, we have to enforce that the energy density is integrable in the vicinity of the edge, so that the stored energy in any neighborhood of the edge remains finite. This is the so-called edge condition, and it was formulated clearly for the first time by Joseph Meixner at the end of the 40s of the 20th century, as you can see in the reference below. For the problem we are considering here, that of a perfectly conducting wedge, by enforcing the boundary conditions on the two sides of the wedge, it is also possible to find explicitly the value of this exponent ni, which is known as the singularity exponent. And in particular, this exponent is given by the formula here above, pi divided by 2 pi minus alpha. So that for the Sommerfeld problem, in which we have a half plane with a 0 internal angle, alpha is equal to 0, and therefore the singularity exponent is equal to 1 over 2, so 1/2. So we can say that EY goes asymptotically in the vicinity of the edge as rho to 1/2, whereas the magnetic field components and also the surface current density, which is related to the magnetic field, they all go as rho to minus 1/2, so that they are actually singular in the vicinity of the edge, because they go to infinity. However, their square is still integrable in a plane, and therefore the magnetic energy remains finite in the vicinity of the edge. Rho is, of course, the radial distance, so it's the square of x squared plus z squared. Okay, furthermore, we may observe now that for the Sommerfeld half-plane problem, the scattered field is produced by the current density that exists on that half-plane, and that current density is purely tangential, since it is parallel to the edge of the half-plane. So therefore, the plane z equals 0 is a symmetry plane for the scattered field. In particular, it is easy to show that the scattered field has an even symmetry with respect to this symmetry plane, which means that the y component of the electric field, which is parallel to the z equals 0 plane, must be an even function of z. In particular, if you evaluate it at minus z, the value you obtain is the same as the value you would have at z, so on the other side, if you mirror the coordinate with respect to the z equals 0 axis. So basically, what we need to know is the scattered field only in a single half space. For example, in the half space where z is greater than or equal to 0. Okay, so in our configuration, the right half space. But there is even more than that. Since we are dealing with the problem of diffraction by screen, in any problem like this, we can decompose the problem into two steps. The first one is the so-called interaction problem, which consists in finding the scattered field on the plane where the screen is located, in this case, the plane z equals 0. And since in our case, the scattered field is actually known on the perfectly conducting half plane, because we know that there it must be equal and opposite with respect to the incident wave, the incident electric field, which is known, then the only unknown that remains to be determined is the scattered field on the remaining half plane, so the half plane where x is negative. So the part of the half of the plane z equals 0 where there is no metal. Then the second step is the so-called propagation problem, which consists in determining the field in the entire half space z greater than 0, that is beyond the screen, from the knowledge of the field on the aperture field, on the aperture plane. That's the so-called aperture field. And we may note that the difficulty is basically the first step, that is finding the field on the aperture plane, because once you know the field on the aperture plane, it is a standard task, that of deriving the field in the entire half space, which consists in evaluating the usual radiation integrals that you may be familiar with from basic antenna courses. Some further remarks before entering the solution. This problem, this Sommerfeld problem, can be generalized in different directions. For example, if we know the solution for the incident wave, which is TM polarized, then we can easily obtain the solution for the dual polarization, that is for a plane wave that is TE polarized, which means that now the magnetic field would be parallel to the edge of the half plane. That is because, as you know, there is a powerful theorem, the theorem of Babinet, which relates the two configurations, which are basically dual or they can be treated as if they were dual. Actually, the duality would involve changing the perfect electric conductor with a perfect magnetic conductor, but Babine allows also to switch the vacuum with the metal. And so at the end, one possible formulation of the Babine theorem is that the one that is reported below in the box, where you can see that the total TE field, the electric field beyond the screen, can be obtained in terms of the incident and total TM field, magnetic field. So once you know the solution for the TM polarization, it's immediate to find the solution for the TE polarization, which is the first generalization. The second one involves changing the direction of propagation of the incident waves. That is, we may allow the incident wave to be incident at an oblique angle with respect to the edge of the half plane. So if we now introduce this angle psi incident, which is equal to pi over 2 when the incidence is normal, as we did previously, what you get is that the incident electric field, again for TM polarization, has, in addition to its dependence on x and z, also some dependence on y, which is still an exponential. And in particular, in the exponent, you can see that we have the cosine of this angle psi, which is measured from the edge. So it's equal to pi over 2 when the incidence is normal. Now, if you observe this incident field, apart from the dependence on y, which is an exponential, we also have the dependence on x and z, which can be written compactly, as you can see here in black, as some function of x and z that also depends on frequency through the wave number k0, and on the incident angles, which are now two angles, theta I and psi I. Now, the crucial observation is that this incident field is an eigenfunction of any translation operator along the y-axis. That is, if you translate this incident field, what you get is the same incident field up to a multiplicative constant. This is an immediate consequence of the properties of the exponential that expresses the dependence on y. And now, since the structure is also translationally invariant along the same axis, we must conclude that also the scattered field must inherit the form, the functional form of the incident field. In particular, it must exhibit the very same dependence on y, this exponential here, times some generally much more complicated dependence on the x and z coordinates. There is this second factor that depends also on frequency and the incident angles. This observation allows us to compare the problem of incident of normal incidence with that of oblique incidence in the next slide. In particular, for normal incidence, the problem is the one we posed before with the two-dimensional Helmholtz equation outside the half plane and the boundary condition on the half plane that involves the exponential that depends on x. Now, at oblique incidence, what we may write down is again a two-dimensional Helmholtz equation. However, now, in place of the square of the free space wave number k0, we have the square of a transverse wave number k sub t, which is defined as k0 times the sine of the incident angle psi I. And if you write the boundary condition, then the boundary condition now involves kt instead of k0, all the other things being the same as in the problem of normal incidence. So all in all, the two mathematical problems are exactly the same. The only thing we need to do is to replace k0 with k sub t, which means that if you know the scattered field for normal incidence, then you may immediately evaluate the scattered field for oblique incidence, because what you need to do is to evaluate the scattered field for normal incidence at a scaled wave number, k0 prime, which is equal to our transverse wave number, that is k0 times the sine of the incident angle psi I. Here you see pi over 2 because we are considering normal incidence, and theta I as further arguments of the scattered field on the right-hand side. And by the above considerations, this must be also equal to the scattered field for the wave number k0 and oblique incidence, that is the left-hand side in the box. Okay, so basically, we need to solve a problem of normal incidence with a scaled wave number, or which is the same, a scaled radiant frequency, omega prime, that is equal to omega times the sine of the incident angle psi I. So from now, we can limit our attention to the normal incidence case and the TM polarization, since once we know the solution to this problem, we are able to treat any polarization and any incident angle. Having said that, we are ready for illustrating the solution that Professor Gori found for the Sommerfeld-Half plane problem, that is a solution in terms of elementary cylindrical waves. Consider, to start with, this elementary cylindrical wave that contains some amplitude term, E0, then a dependence on rho, which is given by the exponential E2 minus J. And finally, the dependence on the angle phi, which is the sine of phi over 2. This solution is, you can check immediately, this is a solution of the two-dimensional Helmholtz equation in cylindrical coordinates, rho and phi, in the entire plane, where phi goes from 0 to 2 pi, okay? And actually, this is a solution that can be thought as being obtained from the method, with the method of separation of variables, since it is the product of two terms. One is a function that depends only on the radial coordinate rho, and it is actually proportional to the Hankel function of order 1/2, and of the second kind, which is something I forgot to write down here. And then there is this second factor that contains the dependence on phi, which is a simple trigonometric function with order 1/2. So basically, what we have is an anisotropic cylindrical wave, since the amplitude of this wave depends on the polar angle phi. The order of this cylindrical wave is also the order of the Hankel function. It's 1/2. Let us examine the main features of this elementary wave by calculating its magnetic field from the first Maxwell equation. We find that the magnetic field has two non-zero components in cylindrical coordinates. They are h rho and h phi. In particular, h rho as the expression reported here, where you should focus your attention on the dependence on phi, which is the cosine of phi over 2, whereas h phi has a dependence on phi as the same dependence on phi as the electric field. That is, we have the sine of phi over 2. Now, since for h rho we have a cosine function, you can see immediately that this function is discontinuous when phi is equal to 0 or 2 pi. Because if you evaluate the cosine in phi equal to 0, then you get a value that is the cosine of 0, that is 1. Whereas if you evaluate this function when phi is equal to 2 pi, what you get is the cosine of pi, which is instead equal to -1. So there is a discontinuity in correspondence of the perfectly conducting half plane. Whereas h phi, as well as EY, they are continuous everywhere, because also on the perfectly conducting half plane, this function, the sine of phi over 2, is equal to 0, both from positive or negative values. That is, if you approach the half plane from phi equals 0 or phi equal to pi. This in turn means that we may evaluate the surface electric current that flows on the half plane by evaluating the jump of the component h rho, which is the discontinuous one, and the result is this one. you see that there is a non-zero surface electric current only on phi equals 0. That is the place where we have the discontinuity of the magnetic field. So this is the crucial observation that Gori made. Since this is the only place, the half plane phi equals 0 is the only place where we have a non-zero surface electric current, which is the source of this elementary cylindrical wave, we may try to solve the interaction problem for the Sommerfeld half plane problem by looking for a superposition of an infinite number of these kind of half integer order cylindrical waves, all these waves having their axes parallel to the edge of the half plane. That is, we wish to write the scattered electric field, as you can see in this formula, as an integral superposition of these elementary waves. As you can see now, here there is an integration variable, psi. So this is an elementary cylindrical wave of order 1/2, centered on the abscissa x, okay? Or better, centered on the abscissa psi, if you prefer, with an amplitude that depends on psi, and we integrate over psi, considering only values that go from x to plus infinity. It is because we know that on the half plane phi equals 0, the electric field produced by these elementary waves are 0. So basically, if you consider a point on the z equals 0 plane at some abscissa x, then a contribution to the field at this point will be given only by the positions, the points on the same plane that are located on the right of that observation point. That is for values of psi larger than x. Now, here, this function p, this amplitude function, is an unknown, and we wish to find this unknown in such a way that this scattered electric field is equal and opposite everywhere on the perfectly conducting half plane in order to satisfy the boundary condition of our problem. And this allows us for enforcing an integral equation in which this function p is the unknown. In particular, the integral equation is the one reported here in the box, where you can see the opposite incident field on the right-hand side. And on the left-hand side, you have this integral superposition of elementary waves. Now, this integral equation can actually be solved in a very straightforward way with a few steps. In particular, you may change variable in the integral. So to integrate from 0 to infinity, this involves writing x prime plus x in place of the old integration variable x, okay? And once you have done this, so once you have an integral from 0 to plus infinity, in order to recover the exponential at the right-hand side from the integral on the left-hand side, with a moment thought, you will find easily that by inspection, the right function to be inserted for p is a simple exponential function that depends on psi exactly as the right-hand side of the integral equation. And in fact, if you replace psi here, the bottom, with psi prime plus x, what you get once you insert it into the modified integral equation that you can see here in terms of the new variable psi prime is that the dependence on x can be brought outside the integral, and this therefore matches with the dependence on x that is found on the right-hand side, and they can be simplified from the equation. And what remains is just this equation in which now x is not present anymore as a variable. We have only an integral with respect to psi, an unknown constant c, and again a constant on the right-hand side equal to 1. So now what we need to do is only to evaluate this integral which can be done by a simple change of variables. Again, if you introduce a new integration variable mu, such that mu squared is equal to k0 psi prime times 1 plus the sine of the incident angle, and if you make this necessary replacement inside the integral, you will manage to cast the integral in the form of a complete Fresnel integral that we have evaluated in our second lesson by means of Cauchy theorem, and the result is the one reported here below, so that finally we are able to evaluate the constant c in terms of elementary functions, that is k0 divided by the square root of pi times e2 plus j pi over 4 times the square root of 1 plus the sine of the incident angle theta I. So now we know basically the field everywhere on the aperture plane z equals 0. That is because when we are on the perfect conductor, we know that the scattered field is equal and opposite to the incident field. That was our boundary condition. Whereas if we are on the remaining portion of the plane, of the aperture plane, where there is no metal, our solution has brought the appearance of this function f, which is the so-called complex Fresnel integral. And so we have basically solved the interaction problem. Note that the argument of the Fresnel integral depends on x. So this is the dependence on x of the aperture scattered field where there is no metal. Once we know the scattered field on the aperture plane, we may employ standard radiation integrals, as I was mentioning before, to obtain the field everywhere in space. Or in this specific case, alternatively, we may also employ the fact that we have constructed our scattered electric field by a superposition of elementary cylindrical waves of order 1/2. So we may resort to this very same representation to obtain the field everywhere beyond the screen, that is for z larger than 0, by enforcing this superposition again. So you can see here the amplitude function p that we now know. Then there is the rho dependence of the elementary wave that now originates from psi, so it depends on rho prime, which is the distance of the observation point from the general point psi on the back plane. And then there is the angular factor, which is also defined in terms of this phi prime angle, which is measured with respect to this point psi. Okay, so this completes basically the elementary solution of the Sommerfeld half-plane problem that was found by Professor Gori. And now perhaps we may have a 10 minutes break before entering the other approach, that is the one based on the so-called Wiener-Hopf method in the formulation based on dual integral equations. So even if it's a bit early, maybe it's better to break the lesson now. So I will stop and see you in 10 minutes. Okay, here we are. We can start again. Now I will show you how to solve the SommerfeldHalf plane problem using the Wiener-Hopf method, which is a powerful method which can be employed to solve also many other diffraction problems, in particular, but not only, problems involving half planes in which the half plane is not necessarily perfect conductor, as we will see in the next lesson, but it can be modeled as an impedance boundary, or there is employing impedance boundary conditions, or also impedance transition conditions. And also the so-called two-part impedance plane. There is a plane which is divided into two half planes, in each of which a different boundary condition holds. I don't know why this small hand has changed its shape. However, okay, let us see in a nutshell what the method consists of. Basically, the solution, the analytical solution of the integral equation that you get by enforcing a boundary condition can be obtained with the method of Wiener-Hopf in two steps. There is taking first the Fourier transform of the integral equation, and then, in the second step, reducing the integral equation to a specific kind of functional integral equation, which is then solved analytically by using specific properties of analytic functions. And in particular, the crucial property that is employed is the so-called Liouville theorem that we introduced in the second lesson of this course, in its generalized form that we did not treat explicitly, but you can find easily anywhere, for example, on Wikipedia. Now, the crucial step in this method, as we will see, consists in factorization of a given function into the product of two analytic functions that are also, in addition to being analytic, that are also without zeros in the upper or the lower halves of the complex plane. So for this reason, the method is also known as the factorization method, and this is a name that is used especially in the Eastern Soviet literature. A mathematical equivalent way of stating the Wiener-Hopf method, but is somewhat more direct, was introduced by Clemau, as I was mentioning before, at the beginning of the 50s, and it's based on the so-called dual integral equation method. And this is the approach that I will describe explicitly, with reference in this lesson, again, to the Sommerfeld-Half plane problem, in which the half plane is assumed to be a perfect conductor. Now, I will change the reference system. Now, X is again along the plane. However, now the edge of the half plane runs along the z-axis, which is therefore the direction of invariance of our configuration, whereas Y, the y-axis, is orthogonal to the half plane. The incident field is again Tm, which means that its electric field has a single non-zero component parallel to the edge. In this case, therefore, it is parallel to the z-axis. And phi 0 is the incident angle, so that the exponential of the incident plane wave can be written in polar coordinates, as you can see here, e to j k0 times rho times the cosine of phi minus phi 0. What I will tell you is basically taken from this beautiful book by Thomas Senior and John Bolakis, Approximate Boundary Conditions in Electromagnetics, which is very advisable if you wish to learn about both the boundary conditions in general, their formulation and use, and also their application in the Wiener-Hopf method, and also the Maliushinets theory for scattering by impedance wedges, and many other things. Okay, basically, we start, or better, Clemau started with a specific representation of the electromagnetic field, which is based on the so-called angular spectrum. Let us focus on our unknown, which is the scattered field, and let us represent both the electric and magnetic scattered fields, in particular the Z component of the electric field, which is the only non-zero component of the electric field, and the X component of the magnetic field, in terms of suitable integrals made in the complex plane of the alpha variable, of the product of the exponential that describes the propagation of a plane wave that propagates along the direction alpha. So you can see here e2 minus j k0 rho times the cosine of phi plus or minus alpha. So we have a plane wave that propagates in the direction plus or minus alpha, times an amplitude function p sub e that depends on alpha through the cosine of alpha. E0 ei, that is the amplitude of the incident wave, has been factored out, has been taken explicitly outside of the integral for convenience. Now, if you use Maxwell equations, you will find the magnetic field directly from the electric field, and you will discover that the X component of the magnetic field can be written in terms of a similar integral, in which, in addition to what we have for the electric field inside the integral, we also have this sine alpha factor. And in addition to that, you have a plus or minus sign in front of everything, and you have to divide the amplitude by the free space characteristic impedance. So this representation basically tells us that if you observe the current that flows on the perfectly conducting half plane, and in particular, more generally, if you have a current that lies on the plane y equals 0 and is directed along the z-axis, as you can see in the drawing below, where the current is represented by those circles, dotted circles, because the current flows parallel to the z-axis in the direction of the observer, that is, it is orthogonal to the plane of the drawing. Then those currents will produce waves, elementary plane waves, that will propagate along any angle alpha. And in particular, if you consider a single plane wave that goes along the angle alpha or minus alpha, the situation for the fields is the one depicted here, in which the electric field is parallel to the z-axis, and it's represented in red, whereas the magnetic field lies in the plane, the xy plane. And if you observe in particular the X component of this magnetic field, you will see that this component for the two plane waves represented here, the one that propagates along the angle alpha and the other one that propagates along the angle minus alpha, well, the X component of the magnetic field of those two plane waves are equal and opposite, and this justifies the plus and minus sign in front of the analytical representation for the magnetic field. Okay, this kind of angular spectrum representation can be justified in many ways. One possibility is to consider the field that is radiated by the surface current in the space domain. We employ the two-dimensional Green's function of the problem, which is here reported in blue. Since we are dealing with a two-dimensional problem, the free space Green's function is proportional to a Hankel function. If you work in cylindrical coordinates, a Hankel function of order 0 and of the second kind, whose argument is k0 times the radial variable that goes from the source point located at x prime on the plane y equals 0. And this is the distance from the source point to the observation point with coordinates x and y. This is basically a superposition integral, and it is actually a convolution integral, since our structure has a translational invariance along the x-axis, in which you superimpose the contribution given by each elementary surface current Js, which is directed along z, and is located at the general abscissa x prime. You integrate, of course, over all the possible values of x prime, that is from minus infinity to plus infinity in general. In particular, if you evaluate this scattered field on the plane y equals 0, what you get is explicitly a convolution, that is the convolution between the function that expresses the surface current and the Hankel function evaluated at k0 times the absolute value of x. Since this is a convolution, if you perform a Fourier transform with respect to the x variable, that is, if you go to the spectral domain, and this is indicated with a tilde over the various quantities, what you get is that the Fourier transform of the scattered electric field is proportional to the product of the Fourier transform of the current, of the surface current, times the Fourier transform of the Green's function. This is the blue term here. This is simply 1 divided by 2j ky, where ky is the vertical wave number, and by the separability condition, this is equal to the square root of k0 squared minus kx squared. This is a quantity that is positive whenever kx is not larger than k0, and this is the part of the spectrum that contains propagating plane waves. Whereas it is imaginary, and this has been written explicitly here by switching the order of the two terms inside the square root, whenever kx is larger than the free space wave number. So we have an evanescent spectrum that is a spectrum of waves that decay vertically, because now the wave number ky is purely imaginary, and they propagate along the plane y equals 0. In any case, once we know the spectrum of the scattered field on the plane y equals 0, it is immediate to obtain the spectrum everywhere else by restoring the dependence on y, that is by inserting the exponential dependence e2 minus j ky times the absolute value of y. So that finally, if we inverse Fourier transform, what we get is the electric field in the space domain, that is as a function of x and y. This is given by an integral, that is the inverse Fourier transform, which contains the spectrum of the surface current, the free space Green's function, that is this ratio here, the exponential divided by ky up to constant, that is 2j, which has been brought outside the integral, and finally the exponential that comes from the inverse Fourier transform, so e2 minus j kxx. Now, we could make a change of variable by introducing a normalized wave number, lambda, that is equal to kx divided by k0, or also by introducing an angular variable, alpha, that is defined here in terms of kx, which is equal to k0 times the cosine of alpha, so that by separability, ky can be written either in terms of lambda as proportional to the square root of 1 minus lambda squared, or in terms of the angular variable alpha as k0 times the sine of alpha. Okay? So in the complex lambda plane, where lambda again is a normalized version of kx, what we have in terms of singularities is a pair of branch points at plus and minus 1. Those correspond to the normalized values of the free space wave number, k0, plus or minus k0. When you divide by k0, you get plus or minus 1. The associated branch cuts, those wiggly lines, which are the standard Sommerfeld branch cuts, and they run along the real and imaginary axis. There is also, in addition, a pole that we will discuss later. It is located there in minus lambda 0. Alternatively, if you employ the angular variable alpha, you should integrate not on the real axis, which is the integration domain of the inverse Fourier transform, but rather on a path that partially runs along the imaginary axis, in particular the entire negative imaginary axis. Then it goes from the origin to pi by avoiding the pole, which is now located at pi minus phi 0. And finally, it goes up to infinity parallel to the imaginary axis with abscissa equal to pi. So this is the integration path C if you employ the angular variable alpha. Now, let us insert this new variable alpha inside the inverse Fourier transform representation of the scattered electric field. What we get is that the argument of the spectrum current is now k0 times the cosine of alpha, and we also have the cosine and sine of alpha in the exponential that describes the propagation of the plane wave. Now, this exponential can be written more compactly by writing the exponent as being proportional to rho times the cosine of phi minus or plus alpha. But what's more important, we may recognize that this term in red here is a function of the cosine of alpha, which is equivalent to what we have written before as the amplitude of the incident wave times the function p sub e of cosine of alpha. So basically, this kind of integral is a modified version of an inverse Fourier transform in which we have introduced an angular variable of integration and in which we can recognize the angular spectrum function p sub e. And once we have this representation for the electric field, the Maxwell equations lead to the representation for the magnetic field that we discussed before. Okay, so this is to justify the angular spectrum representation of the field. This is our starting point. Alternatively, you could also use the normalized wave number lambda, and in that case, for the electric field, you would have inside the integral, which is now performed on the real axis in the lambda plane, you would have the explicit appearance of the denominator with the square root of 1 minus lambda squared, whereas in the magnetic field, this denominator is not present because it's simplified with a similar term. And so you only have the spectral function p sub e in addition to the spectral integrals. Okay, now let us enforce the boundary conditions. Since we want to solve the Sommerfeld problem, we write the scattered electric field on the plane y equals 0 using the lambda variable. And the boundary condition is that the total tangential electric field must vanish on the perfectly conducting plane, which means that the scattered field here in the box on the left-hand side must be equal and opposite to the incident field. Here in this equation, we have also simplified the incident amplitude E0I, so you do not see it appear explicitly. This is an integral equation that holds not on the entire y equals 0 plane, but only where the metal is present, that is, only where x is positive. On the other hand, let us see what happens to the magnetic field. Now, the magnetic field is an odd function of y, as you can see directly from its spectral representation, or also from physical considerations. In particular, if you evaluate the magnetic field on the plane y equals 0, what you get is that on the plus side of this plane, that is when y is equal to 0 plus, this is the expression you get that is equal and opposite to the expression of the magnetic field on the other side of the same plane, that is where y is equal to 0 minus. But from the boundary condition for the magnetic field, we know that the jump of the magnetic field is related to the surface current. So since this surface current exists only on the metal half plane, what we get is basically that where the metal is not present, that is when x is less than 0, the scattered magnetic field must be equal to 0, since it is an odd function, and it's equal to 0 since there it has no discontinuity. So from the spectral representation of the magnetic field, we have that the magnetic field, that is the integral here on the left-hand side in the box, must be equal to 0 whenever x is negative. So this is another integral equation that holds where the metal is not present. The same integral equation can be obtained with a different approach by recalling that our spectral function, the function p sub e, is proportional to the spectral current J tilde. So that if you inverse Fourier transform the spectral current, you obtain the current in the space domain. This is what you get. An integral of PE of lambda times the exponential of any inverse Fourier transform. But again, this current density is non-zero only where the metal is present, that is when x is positive. So that again, if you evaluate this integral when x is negative, the result must be equal to 0. So we again have an integral equation that is valid when x is less than 0. So all in all, what we have is a pair of integral equations. The first one enforces the boundary condition on the electric field when X is positive, that is where there is metal. The other one enforces the vanishing of the scattered magnetic field where the metal is not present, that is when X is negative. Now, this is a system of integral equations which share the same unknown, which is the spectral function P sub E of lambda. However, those two integral equations hold in different domains, in particular into two complementary half planes. And furthermore, they have different kernels, because you can see that in the first integral equation, you have this square root function in the denominator, which is absent in the second integral equation. When you have a situation like this, you have a system of dual integral equations. This is the terminology. Okay? And what we will do in the remaining part is that we will solve these dual integral equations by using complex analysis. First of all, let us prove that the spectrum is an analytic function in the upper complex plane. To do so, let us recall that the spectral function P sub E of lambda is related up to a constant to the spectral current J tilde, that is, to the Fourier transform of the spatial current J as a function of X. Okay? Now, this current is non-zero only where we have metal. So, in performing this direct Fourier transform, that is this integral with respect to X, we may integrate only when X on the domain where X is positive. So, we can integrate only from 0 to plus infinity. Now, whenever you have a Fourier transform of a function that is defined on a half line, that is where X is positive, you can integrate this Fourier transform, in particular the function P sub E of lambda, along an arbitrary closed contour in the upper lambda plane, that is the integral with this small circle on it, performed on this arbitrary contour gamma. And what you get is a double integral, in which the outer integral is performed as a contour integral in the complex lambda plane, whereas the inner integral is an ordinary Fourier transform performed by integrating only on the positive x-axis. Now note that since x assumes only positive values, the exponential function that is contained inside the inner integral is a function that tends to 0 exponentially when x goes to plus infinity, if lambda is a complex number with a positive imaginary part, that is, if we are working inside the upper half plane of the complex lambda plane. If we are integrating in that half plane, therefore, the inner function is integrable, and we can use the theorem of Fubini and Tonelli, which allows us to reverse the order of integrations. That is, we can perform the integral with respect to lambda as the inner integral, rather than as in this formula, the outer integral. But if you do so if you bring the integration with respect to lambda as an inner integral, what you remain is just the exponential function, which is the only thing that depends on lambda. And now the exponential function is analytic everywhere. So if you integrate along any closed contour by Cauchy theorem, this integral will be equal to 0. So what we have obtained is that any integral of our spectral function made with respect to a closed contour contained in the upper half plane is equal to 0. Now, we can use Morera's theorem, which you may remind is a sort of converse of Cauchy theorem. Morera's theorem says that if you know that your function integrates to 0 along any closed contour, then that function must be analytic. So we may conclude that our spectral function is analytic in the upper half plane of the complex lambda plane. To make this evident, we will make a change of names. We will, from now on, call this unknown function P sub E of lambda with a new name, that is as u of lambda, where u stands for upper. This reminds us that we are dealing with a function analytic in the upper lambda plane. Now, note that if you now close the integration path by an infinite semicircular contour in the upper half plane, and this is possible again because x is less than 0, then since the spectrum we now know is an analytic function, and by means of Cauchy theorem, we may conclude that the integral of u of lambda times e2 minus j k0 x lambda, evaluated by closing the contour at infinity, is equal to 0. And therefore, the second integral equation of our system of dual integral equations is identically satisfied. So the analyticity of the spectrum by itself guarantees that one of the two integral equations is satisfied. So what remains is the first integral equation, the one that comes from the boundary condition on the electric field. Now, to solve this integral equation, we will again close the integration path at infinity by means of an infinite semicircular contour. However, this time we will do that in the lower half plane, because this integral equation holds for positive values of x. So to make the integral convergent, we will close the integral along the lower half plane, in the lower half plane. In order to obtain a non-zero value, because now the right-hand side is different from 0, we have an exponential function. So we wish that closing the integration path at infinity in the lower half plane, the result of the integrating along the closed contour must be the right-hand side, that is an exponential function. So this means that the function we are integrating cannot be analytic in the lower half plane, otherwise the result would be identically 0. Rather, it should have a singularity, for example, a pole, such that the residue evaluated at that pole will reproduce the right-hand side of this integral equation. So this is the reason why we will write the function that appears inside the integrand, that is this ratio between u of lambda and the square root of 1 minus lambda squared, in this form here in the box, where you can see, consider first this ratio, 1 divided by lambda plus lambda 0. This is a term that introduces a single pole in the lower half plane at lambda equal minus lambda 0. And lambda 0 is the cosine of phi 0. That's the so-called optical pole. We enforce the presence of this term because this establishes the existence of a pole whose residue must reproduce the exponential function on the right-hand side of the integral equation. And this exponential actually comes out from the exponential that is inside the integral on the left-hand side once you replace lambda with cosine of phi 0, which is actually the value of lambda 0. That is the value of lambda at the pole location. In addition to this term, the one that produces the pole, we also have the constant 1 divided by 2 pi j. This is introduced in order to simplify the term 2 pi j that occurs from an application of the residue theorem. In addition to that, we may allow any analytic function in the lower half plane to exist in the numerator, because this does not change the property that there is a pole at the right location. So we may let L1 be an arbitrary analytic function in the lower half plane in the numerator. However, if we introduce that function in the numerator, we must also compensate by introducing a constant, which is L1 evaluated at minus lambda 0, so that the residue at the pole does not change. In addition to that, if you add a second arbitrary analytic function L2 in the lower half plane to the right-hand side, this does not change anything because the integral of that function evaluates to 0 by Cauchy theorem. So basically, this is the form of our function u given that it must reproduce the right-hand side of the integral equation. Note that in this box, we have actually three unknowns. There is our spectrum, the upper function u of lambda, and the two lower functions, L1 and L2, which are analytic in the lower half plane. And this is a functional equation in three unknowns. However, by means of complex analysis, we will be able to find all these functions, and now I will show you how. The approach is based on the so-called splitting of the functions that appear in this functional equation. That is, in the representation of those functions as the product or splitting of two factors. In particular, if you have a function f of lambda, the splitting produces the representation of the function as the product of two functions, f plus and f minus, where f plus is the so-called upper split function and f minus is the lower split function. Those functions are both analytic and free of zeros in the upper or lower half planes. For example, in our problem, on the left-hand side of this functional equation, the numerator is an upper function, so we don't need to do anything with this. The problem is the denominator, that is the square root of 1 minus lambda squared. This is neither upper nor lower, but it can be decomposed as the product of two factors, the square root of 1 minus lambda and the square root of 1 plus lambda, the first one of which is an upper function, k plus, because if you observe the situation here in the complex lambda plane, you will see that the branch point at 1 can be considered to lie in the fourth quadrant. That is, if you introduce infinitesimal losses in the media, the wave number will be removed from the real axis and it will go into the fourth quadrant of the lambda plane. So therefore, the function square root of 1 minus lambda is analytic in the upper half plane. And for the same reason, the function square root of 1 plus lambda, which has a branch point at -1, if you introduce infinitesimal losses, this -1 will go into the second quadrant, and therefore this function k minus is analytic in the lower lambda plane. So we have been able to split by inspection this function k of lambda, which is the square root of 1 minus lambda squared. So if you insert this splitting of the function k inside this equation here, this functional equation, and you leave all the upper functions on the right-hand side, and you bring the lower functions on the left-hand side, on the left-hand side, and you bring the lower functions on the right-hand side, what you get is this, in which you have on the left-hand side u divided by k plus, and those are upper functions. And on the right-hand side, you have only lower functions, that is L1, L2. Is an exception. We still have the optical pole at minus lambda 0, which is not a lower function because the pole lies in the lower half plane. So we have to remove this pole from the right-hand side. In order to do that, what we need to do is just to subtract a suitable quantity from both sides. And the suitable quantity is the one that you can see here on the left-hand side. It's 1 divided by 2 pi j times k plus evaluated at lambda 0 divided by lambda plus lambda 0. That is because if you do that the same, of course, on the right-hand side, what you get is that the term that contains the pole, 1 divided by lambda plus lambda 0, gets multiplied by this square bracket. And inside the square bracket, what you now have is something that is equal to 0 when lambda is equal to minus lambda 0. So if you evaluate the residue of this term on the right-hand side, the residue is now 0. So the pole is actually not there anymore. So we have brought the pole on the left-hand side. And so finally, we have a left-hand side that is an entirely upper function with a right-hand side that is an entirely lower function. And we are now close to coming to the conclusion. The only remaining step is to examine the behavior of both sides of this equation at infinity. That is, when lambda has very large values in absolute value. Well, the behavior of the spectral function u when lambda goes to infinity can be evaluated asymptotically by using Watson's lemma, by recalling that our spectrum u is nothing but the Fourier transform of the spectral current up to multiplicative constants. And the spectral current, J tilde, is the Fourier transform of the current J. If we know the behavior of the current in the vicinity of the edge of the half plane, then by Watson's lemma, we will be able to find the behavior at infinity of its Fourier transform. But we know the behavior of the current near the edge from the edge condition that tells us that for a perfect conductor, we have a behavior like x to minus 1/2. So by Watson's lemma, we will have that the spectral function J tilde, and therefore also the spectrum u, will go at infinity as lambda to minus 1/2. So we may now examine, for example, the left-hand side of our functional equation, that is u divided by k plus minus the term containing the optical pole. U goes to infinity like lambda to minus 1/2. The same is true for k plus, which is the square root of 1 plus lambda, 1 minus lambda, sorry. So it goes to infinity as lambda to plus 1/2. So all in all, this ratio goes to lambda to minus 1, exactly as the term with the optical pole does. So the entire left-hand side of our functional equation goes to infinity as lambda to minus 1, which means that it is infinitesimal at infinity. So this is now the crucial step, and we can collect all the information we have gathered so far. We had a functional equation, this one, in which the left-hand side is an upper function that is analytic in the upper half plane, and the right-hand side is a lower function that is analytic in the lower half plane. But those two sides are equal, as the equation tells us, so they must both be upper and lower functions simultaneously. So they are analytic everywhere, so they are entire functions of the complex variable lambda. Furthermore, we now know that they are also infinitesimal at infinity, because they go at infinity as lambda to minus 1. And since they are infinitesimal at infinity, they are bounded functions. So we have entire functions that are also bounded functions. And now we can employ Liouville theorem, which tells us that if you have a bounded entire function of a complex variable, then that function must be equal to a constant. And since those functions are infinitesimal at infinity, the value of such a constant must be equal to 0. So basically, we can equate to 0 both the left and the right-hand sides of our functional equation. If you do so with the left-hand side, what you get is the equation written here in the bottom part of this slide, that is u divided by k plus minus 1 divided by 2 pi j times k plus evaluated at lambda 0 divided by lambda plus lambda 0 equal to 0. And note that in this equation, the only unknown is u of lambda, so that you can now solve with respect to u to obtain an explicit expression for u, that is, for the spectrum p sub e of lambda. This is equal to 1 divided by 2 plus pi j times k plus of lambda times k plus of lambda 0 divided by lambda plus lambda 0. And if we recall what's the definition of k plus, it was the square root of 1 minus lambda, we get this explicit expression for the spectrum in terms of the variable lambda, or, if you prefer, in terms of the angular variable alpha, as you can see here in the box. You have the spectrum p sub e as a function of the cosine of alpha, expressed in terms of elementary functions, because we have square root functions which are evaluated in once with the argument 1 minus cosine of alpha, and another time with the argument 1 minus cosine of phi 0, which is a constant, that is phi 0 is the incident angle. Whereas in the denominator, we have the sum of two cosines, cosine of alpha plus the cosine of phi 0, and this denominator introduces the optical pole. So by using Liouville theorem, this is the method of Wiener-Hopf, we are able to solve a functional equation and thereby finding the spectrum in a closed analytical form, which is rather simple, by the way. And this completes our derivation. So what we have shown is how to solve Sommerfeld problem in terms of a spectral representation of the field, that is in terms of an angular spectrum. And to find an explicit expression for the angular spectrum, we have written down dual integral equations. We have reduced those dual integral equations to a functional equation by employing complex integration techniques. And finally, we have solved the functional equation by means, again, of complex analysis by using the Liouville theorem. Okay? So we have seen a number of complex analytic techniques or theorems orchestrated in order to find an explicit analytic solution to the Sommerfeld problem. And that concludes our lesson of today. Here are the references I have already given you in the previous slides. In the next lesson, we will again address this Sommerfeld problem. However, we will generalize the discussion. First of all, we will treat the scattered field, in the Fraunhofer region. So we will make an asymptotic analysis of the scattered field. And second, we will consider a different kind of boundary condition, that is, we will treat impedance half planes in order to generalize the discussion of today that was devoted to perfectly conducting half planes. And that's all. Thank you again for your attention, and see you on Thursday.
Grazie Paolo, ciao.
Grazie, buona giornata a tutti.
Thank you, bye.
Grazie, buona giornata.
Arrivederci.